Hello everyone, Tony here, and in this video I'll be showing you how you can program PIC-based microcontrollers on a Linux computer. So let's get started. So some of you may be wondering, what exactly is PIC? Well, PIC is a family of microcontrollers. It is an architecture for a family of microcontrollers similar to how all of the Atmel chips are based on AVR, or there are many ARM-based little microcontroller devices as well. PIC is based on a RISC architecture. It is a reduced instruction set system similar to AVR and ARM once again, which makes it quite popular for hobbyist projects. PIC microcontrollers can be used in very similar scenarios to where you would use an Arduino actually. So some of you may be wondering, why should I even use a PIC-based microcontroller when a platform such as Arduino already exists? PIC-based microcontrollers used to be very popular before Arduino took off in popularity if you wanted to just hack together an electronics project quickly. Unfortunately, the PIC architecture has less documentation compared to Arduino, especially nowadays since many people are doing almost all of their electronics projects entirely on the Arduino, which leads to there being lots of libraries and other helpful guides available to you that you can use as a base for you to build your own project. Furthermore, PIC microcontrollers are often programmed in assembly or in C, which are low-level languages. Now, Arduino software is also based on the C language, but it has been abstracted a bit to make it easier. For example, you can use digital write and digital read commands, or like pin modes to set the pin mode. Whereas if you are working directly on the microcontroller, you would actually have to be reading and writing values to memory addresses to be able to get that same functionality. So it's a bit more manual in terms of how you have to work with it. Now fear not, you're not left entirely in the cold. There are lots of header files available for every microcontroller. These are files that contain all inputs and outputs parameters and return values for all of the functions of the microcontroller, as well as all of these required memory addresses for where configuration files are stored. They provide a layer of abstraction, making it easier so that you can just write a config statement to the appropriate memory address without having to know what it is. And it also makes it so that your code is more portable across different devices, because if you switch from one microcontroller chip to another IC, the appropriate header file for that IC will have the appropriate memory addresses for each of the configuration options as well. That being said, since Arduino has become so popular, there are tons and tons of libraries available for the AVR architecture. Unfortunately, most of those libraries would be very hard or impossible to port over. So if you want to get the same functionality out of a PIC microcontroller, you will have to put in a lot more work to get it working with that exact specification. Fortunately, there are lots of standards that are supported universally across microcontrollers. For buses, you have I2C and SPI that can be used to easily interact with peripherals. Certain PIC ICs also have extra features such as built-in USB chipsets. That way you can interface with other USB devices without requiring special programming. So you may be wondering, why should I make my project with PIC? Why should I follow along with this video? Well, if you want to practice some C programming or just dabble your feet in some embedded programming, this would be an excellent starting point. If not, even if you're curious to get into tinkering, or you just want to do something different that's not just an Arduino with a library, if you want to get a little bit more involved in your projects, this would be a great stepping stone to say something like building a custom microcontroller. There are multiple lineups of PIC microcontrollers that you can use for your getting started project. The two main ones would be the 14F and the 16F series these days, and as an extension of the 16F there's also the 18F, but those remain backwards compatible. The 14F feature a 14-bit data and instruction bus, and the 16F are a 16-bit bus. The 18 also contains some extra instructions, but most compilers don't take advantage of them. For this project, I have chosen the PIC 18F2050 for its good combination of features and ease of use. It contains a lot of the features that you would also find on many Arduino chips. This IC has a 12 MIPS 48 MHz processor, 2 KB of RAM, 1 KB dual port, and 1 KB general purpose, 32 KB of flash storage for your program and data. Since it is a microcontroller, there's also plenty of I/O. There are a total of 16 input and output pins. The digital pins can be used as digital inputs or outputs. There's also a built-in 10-channel analog to digital converter with a 10-bit resolution, which is the same resolution as Arduino chips. The pins can also be used for two onboard built-in comparators. There's also plenty of connectivity, including the standard UART, SPI, and I2C buses. There is one built-in 8-bit timer and 3 16-bit timers. The chip features low power consumption and is 3.3 and 5 volt compatible, depending on which makes more sense for your project. As an added bonus, there's also built-in USB, meaning that you can interface with traditional USB devices, albeit it's limited at 12 megabits per second full speed. Some of you might be wondering, well, how exactly are we going to program this? I don't see a USB port here that we can plug in to just send code. Well, that's because this is a bare IC, just like what's included in an Arduino. The difference is, most Arduinos include an onboard USB programmer that lets you upload your programs to the flash storage of the chip. Now, a similar thing exists for a lot of things. For example, to use STM32 boards, you need an ST-Link USB adapter. Similarly, for PIC boards, you need a microchip PIC programmer. So for this, I will be using a PicKit 2. These programmers can be had for cheap, around $10–12 on eBay, depending on when and where you look. Now, there are multiple iterations of the PicKit devices. If you are going to be following along on Linux, I will have to recommend that you stick with the PicKit 2, as the PicKit 3 is not properly supported on Linux due to the lack of open source drivers. If you are not going to be using Linux, you can use whichever programmer of your choice. Let's get into how this works. On one end of the PicKit 2, we have a USB mini B port, and on the other end, we have the 6-pin connector. The 6-pin can be used with a simple ribbon cable to allow you to upload to multiple PIC devices. How these 6 will connect on your IC depends on the exact chip that you are following along with. So, to program this IC, we need to connect the output of the PicKit to the appropriate pins on the chip. The easiest way to do so is to just use some jumper wires from the output of the PicKit 2. The exact pins will change depending on which chip you're using, but you can just look at the pinout that is available for the PicKit 2 and for your IC. To easily match the pins on your IC to the pins on a pinout on a datasheet, there are a couple of guide tricks that you can use. This 18F2550 is a 28-pin chip. Now, the way that IC's pins are usually numbered, you start on this bottom left corner with pin 1, and this goes all the way along the bottom row up to pin 14 in this case. Then you loop around counterclockwise, start again at pin 15, all the way up until the other end where you end at pin 28 in this case. Now, to indicate this, there are 2 little notches. So the first one is there's this notch over here. This indicates the start and end pins. So pin 1 is here, pin 28 is here. And then to indicate which one is pin 1, there's this tiny little circle here embossed into the chip. That circle indicates that this is pin 1. Both of these notches also exist on the datasheet, so you can use that as a reference. As for the PicKit, you will notice that the PicKit has 6 pins on its output. The pin that is right by the arrow is pin number 1, so it goes 1 and then down through 6. Now we can begin to match the pins from the PicKit to our IC of choice. When the PicKit is connected, it actually doesn't activate at first. The PicKit will only power this chip and set the appropriate pins when you're actually uploading a program. This means that during idle time, you still need to power, like if you want to run your program, you will need to provide separate power to the chip. It will not receive it. Now to start connecting the pins, we can connect pin 1, which in this case is this blue ribbon wire, using a jumper wire, to the MCLR, the memory clear inverted pin. So on this IC, and on most PIC ICs, that is pin number 1. So you can connect that like so. Next up, pin 2 is the VDD target. The location of the VDD pin depends based on your IC, VDD being 3.3 volts. For our IC, that is going to be pin 20. Again, look this up for the datasheet for the specific PIC chip that you're using. So, counting pins, you can just connect that right over there to pin 20. Pin 3 on the PicKit connects to pin VSS, which is ground, which in this case is pin 19 of this. Here, I'll move these wires out of the way to make this easier to see. Pin 4 goes to the ICSP data pin. also referred to as PGD. On our IC, that is going to be pin 28, which is over on this end. I've been trying to avoid having overlapping wires, but I think you guys can still see this. And finally, we'll connect to PGC, just like this. Now we are ready to actually upload a program. Alright, now on to the appropriate software. The exact packages that you might have to use will change depending on which distribution you are using. I will just demonstrate it for Arch. So we're going to need two main programs to pull this off. First of all, we need SDCC, which is a small device C compiler. This is a C compiler meant for embedded devices. There are some examples listed here, but it also works on PIC devices and has a very broad compatibility. This is available in the regular community repo, so it can be installed with just a single pacman command. Next, we will need a program to actually upload our hex files to the microcontroller. The easiest way to do this, if you're using a PicKit 2, is with the PK2CMD program. This is available as part of the PK2CMD-plus package on the Arch user repository. You will also need an IDE or a text editor. A text editor like Nano, Vim, or Emacs will work. I'm just going to use Genie, which is a lightweight IDE for many programming languages. So, to get these installed on your computer, you can use an Arch user repo helper of your choice. In this case, I'll be using Trizen. Or you may choose to manually download the PKG build and just run make pkg-si. Alright, now that we have these installed, we can get started. First off, you can plug in your PicKit 2 and just check to make sure it's determined and recognized by PK2CMD. The easiest way to do this is with the PK2CMD-S command. And you should see your device show up and operation succeeded. An excellent starting point for testing out your PIC microcontroller is the SDCC examples repository on GitHub. This repository has a couple of example files for different microcontrollers. For our case, if we hop on under the PIC 16, we can see that we can use the blank LED sketch as a good starting point. I would recommend going through and understanding what's actually happening here, because getting used to the configuration settings for this chip is different than how it works for an Arduino, and you might need the example to get an idea of how it works. Fortunately, we don't have to come up with all of the configuration options by hand, as we can figure out which parameters exist by checking the header file for the microcontroller we are using. The easiest way to do this is to hop on over to the SDCC directory, which is at /usr universal system resources /share/SDCC. Here you will see three main folders: include, lib, and non-free. The IC we are using, the PIC 18F2550, is under the non-free folder. This is because while the source code is distributed, the license that Microchip has unfortunately put over their code means that it cannot be distributed everywhere. So if we go here and we can check under the include folder, we'll see that there's two directories, PIC 14 and PIC 16. We're using a PIC 16 device, so we'll hop on over here. The header file is located here. Now if we run ls or ll, we will see the listing of all the files in this directory. So here we can check to make sure that our chip is supported. There we go. And if we open this file up, we will see the actual header file that will get imported into our programs. Now, this is actually quite sophisticated and complicated, and there are a lot of different parameters here. Let's open this up in our text editor. So here I have this file opened up in Genie, and there's a couple of things here that are of note. So this file defines all of the addresses for different settings or different different commands, anything that we may actually have on the IC. Think of this as the equivalent of your Arduino if you say digital write to pin 10. So because these are memory mapped I/O, what you actually need to do is you need to place a 1 or a 0 in a particular bit of the RAM, which will happen to trigger the digital pin. But when you write pin 10, your program needs a way of figuring out which memory address that actually is in, and that is located in this header file. Similarly, a lot of ports serve multiple purposes. For example, they may be both an input and an output. So once you place the bit to tell it whether it should be an input or an output, if you want to read from the port, it is actually very similar to just reading from that address. So you can see, for example, that under port A, we have the bits by default. Same with port B and the locations, and port C, port E, so on and so forth. So all of that lies here in this header file. If you're not sure what I'm referring to when I say port A, port B, port C, the datasheet will help you out here. So I have the datasheet pulled up here. And if we just scroll down a little bit right to here, we will see the actual pinout of the device. Now after this, you will see that, for example, we have RA, RA1, and there's a nice table down below that indicates what these are. RA is connected to your port A for digital input and output. AN are the different pins connected to the 10-channel 10-bit ADC, analog digital converter. And a lot of pins have to serve multiple purposes, just like they do on the Arduino. For example, pin 21 and 22 can be used for SDA and SCL if you're running I2C, SDI, SCK if you're running SPI, or digital input or output if you're using it under port B1 and B0, or as analog inputs on channels 10 and 12, or as interrupts. So a lot of pins serve multiple purposes. But this gives you the sense of these pins are the ones on port A, port C down here, and port B up here. Now there is a table. So under the block diagram, we have this table that actually explains what each of these pins can be used for. This is on page 14, 15, and 16, 17. So if you're curious about which port you can use to do what, taking a look at this table will probably be a good starting point. For example, under each pin number are all of the functions listed. If you're looking at pin 21, for example, you'll see that it is RB0 on the digital I/O, AN12 for if you're using it as an analog input, INT0 for external interrupt 0, FLT0 for PWM, SPI data in, or I2C data I/O. And up at here, we can see that the configuration for port A. For example, port A is a bidirectional I/O port, so everything on A. Port B is also useful because not only is it bidirectional, but it has internal weak pull-ups. This makes it practical if you're going to use something like a button or USB or I2C or any of the more advanced features. So here we can see all the other functionality. For example, this part can also be used as the timer 1 oscillator or for your timer 1 and 3 external clock. So for example, if you wanted to run the clock at a slower speed, you could use a 555 timer and feed the output here. The exact configuration bits can be found at the end of this header file, under the configuration bits section. These are the locations of all of the different config bits, and under each one we can see the different parameters that are supported. For example, you may want to disable the watchdog timer, you might want to code protect or non-protect different parts of the memory, so on and so forth. So that is all available here. So let's take a look at this example code snippet. In this video, I won't go into how you can actually write your programs, but this should serve as a decent starting point. So after our include statements, we can see we have our fuse start section. So these are all of our configuration parameters. So in this case, we are disabling the extended instruction set. Here we can select FOSC is our oscillator selection. In this case, it is the internal oscillator. Next, we disable the watchdog timer and use single supply ICSP to off. Here we have two lines for the actual bits and the tris. What this does is this sets the pin as an input or output when we write something there. And this will set the LED to be on or off. So hopping over to the void main. Void main is the function that will run when this chip starts operating. We set LED tris to 0, which marks it as an output. This is the on an Arduino. This is equivalent to doing pin mode, the pin number you're using, comma, input or output. Next, we want to turn the LED off. So we will just set the bit to be a 0. Then the while statement, this is a loop. So inside of our loop, we just toggle the LED. Since this is a Boolean, if it's 0, it'll get marked as a 1. If it's a 1, it will get marked as a 0. And next we do delay 1 KTCY. Now, if you're used to an Arduino where you just use delay with the number of milliseconds, this is different notation. That is because this 125 is actually in terms of the system clock. So this translates to roughly 500 milliseconds at the 1 megahertz system clock. In this case, our LED is set to be on pin C0, as it is set by pin LATC and TRISC. So we will use port C0. You can use any of the other ports that support functioning as a digital output as well. You can go with port B0, A0, depending on which pins they map to on your IC. If we're going to be using multiple devices, you might want to be strategic and save the ports that can be used for other functionalities, such as I2C for that. Once you're happy with your program, it is now time to compile it. We can do this by running SDCC. So we will just run SDCC. We need to include the -- use non-free parameter so that SDCC will look at the header file we are using. We want to use the MPIC 16. And the chip we are using. You would replace this for whichever device you are targeting. And we want to compile blink.c. This will be whatever you chose to name your program. We get a couple of warnings, but as every good programmer knows, warnings can safely be ignored. So if we do an ls, we will see that a couple of different files have been generated here. Blink.c was our original file that we chose to compile. Now the first thing that happens is we also get a .asm file. This is the assembler code that the device is going to use. So this starts off with some configuration options that we set in C. And then we have all of our external variables. These correspond to the appropriate addresses for this device. Here we have our internal registers. If we had interrupt functions programmed, they would be under the interrupt vector section, since this IC does support interrupts. And finally, after global and static initializations, we have our actual program. So I won't go into assembly. These used to be the way of programming these chips. Fortunately, we can now have compilers to generate this for us. A semicolon usually represents a comment in assembly. In this case, we will see that SDCC leaves helpful comments here. So for each line that it's converted, it'll put the line number that it was in your source code. For example, line 28 was our LED tris equals 0. And it'll put the exact line that it took, which file it was in, the line number, and the generated assembly. For example, this toggle effect, found on line 32, translates to these assembly instructions. Having the files is useful because when you start getting complicated projects, you can actually have multiple files, and then the linker will merge all of those to one. Now, this isn't actually what we're going to upload though, because the microcontroller only runs on binary files. So for that, we flash the hex file. For example, we can take a look by running xxd on blink.hex. And for us, this looks entirely like gibberish. But for the chip, this is the 1 and 0 sequence, the binary that it will execute on startup. Now, to actually flash our program, we will run pk2cmd, put our IC number, our file that we would like to upload. Remember, this should be the binary file, which is the .hex, and then -m, -r. So now here you can see the actual setup from earlier, and you will see these lights flash when we actually upload this. So let's press enter on our terminal. and you'll see that the target I'm busy starts flashing, and on your screen you will get program succeeded and operation succeeded. This means that your code has been flashed onto this device. Now, to see the result, we have to connect our LED to our IC, and we'll be able to see our blink file. Hopping back over to the datasheet, we can see that port C0, which we use on our IC, happens to correspond to pin 11, as we can see right here. So I'm going to take, this is just a 5mm blue LED. Any output device will work. If you're going to be running your IC at 5 volts, make sure you put a 330 ohm or 220 ohm resistor in series with your LED. I'm going to run the IC at 3.3 volts, such that we don't need any external resistors. Now we do need to connect our chip to ground and 3.3 volts. So we're going to take the input voltage, connect it to our voltage rail. If you're using one of these breadboard power modules, please be careful to connect it to the correct rail. Because if I zoom in here, you will see that the top rail is always connected to ground at 5 volts, but it connects the bottom rail of your breadboard to ground and VCC, where the VCC voltage is selectable by this slider. Make sure you don't accidentally fry any of your components. Unlike other breadboard power modules, which always synchronize the voltage across them, this one does not. So it's just something to be cautious of if you're using this particular model. Now the grounds on any circuit are connected, so which ground connection you use doesn't actually matter. So we can grab pin 11, which is port C0. Connect it to the input of our LED. Just like this. And connect the LED to ground. I apologize for having all the wires be black. I need to get more spools. Here we go. Now we need a power source. Now you will notice that our LED does not light up. This is because you need the memory clear pin connected to 3.3 volts. Once we do this, you can see that our LED is blinking. Now you might note that this is actually quite a bit slower. Well, I assume that is because this IC is operating at a different frequency right now. To change the duration of our LED, we can just plug it back into our computer. Remove this jumper wire that connected M clear. Hop back over here. Change this delay to something like 10, so a value that's quite a bit lower. Hop back over to our terminal, where you can just run SDCC and run PK to CMD again, and you will see your PicKit lights flashing, just like that. And if all is well, you will get the program succeeded and operation succeeded message. Plugging this jumper wire back into 3.3 volts reveals that our LED is now blinking quite a bit faster. There's a whole lot more you can do with these ICs, and this is just the example. There are numerous guides online that can help you actually build more complicated programs should you be interested in that. Since this video is getting quite long already, I'm not going to go into programming. I just wanted to make this because I have found guides for programming on a PIC microcontroller, but I haven't actually found any good starting resources which would help you build up a development environment and actually upload any of your files. So I hope this has helped you get that up and running, especially if you're on a Linux computer and you don't have access to other IDEs such as MPLab. At this point, I would like to thank you all so much for watching. I hope you learned something. I hope this has been a good inspiration for you to maybe start tinkering around with other microcontrollers, or maybe even building your first little project using C, go beyond the example. Let's try something new. Thank you all so much for watching. I hope you have a great day.